This is a tutorial on the mole, and the calculations will be focused on those of elements instead of compounds. So what is a mole? It's defined as a chemical unit which contains 6.022 times 10 to the 23rd molecules, atoms, ions, whatever you want to put in the blank. A mole is used to relate the atomic and molecular scale, that submicroscopic scale that we can't see, to a laboratory scale where we can actually make some concrete measurements. But a mole is really just a number of things. If we say a dozen, we mean there are 12 things. A mole means there are 6.022 times 10 to the 23rd things. It's the same concept, just that number is just significantly larger. That 6.022 times 10 to the 23rd number is Avogadro's number. How do we know when we have a mole? We could count it out and see when we have 6.022 times 10 to the 23rd, or we could just weigh it out knowing that we can relate the laboratory scale to the molecular scale using moles. So which way would we rather do it? We would obviously want to weigh it out because that's going to be something that's easily measured, and counting up Avogadro's number of anything would just be way too time consuming and not a practical thing to do. The molar mass of an element is going to be the atomic weight or atomic mass of the element in grams per mole. For example, hydrogen has an atomic weight of 1.00794 grams. That is, that number of grams of hydrogen atoms would equal 6.022 times 10 to the 23rd hydrogen atoms. Magnesium has an atomic weight of 24.3050 grams, which means that many grams of magnesium atoms represents Avogadro's number of magnesium atoms. Notice the masses are different, but the number of atoms remains the same, and that's because each individual atom has different masses. This is a flowchart indicating converting of atoms and molecules to moles to grams. So again, it's back and forth between that atomic and molecular scale to a laboratory scale using moles. So we get atoms and molecules. We can multiply or divide by Avogadro's number, get moles, and then we could use molar mass to get grams. So this region here between atoms and molecules and moles, we would multiply by Avogadro's number to convert moles to atoms, and we divide by Avogadro's number to get from number of atoms to moles. This other region, we go between moles and grams. We'd multiply moles by molar mass to get grams. We divide by molar mass to get moles. Now, can we do this and go directly from atoms to grams, or vice versa? No, we cannot do that. You have to go through moles. So let's look at an example here. We want to know how many magnesium atoms are contained in 1.67 moles of magnesium. So if we take the 1.67 moles of magnesium atoms given in the problem, here we're going to multiply by Avogadro's number to get number of atoms. Noticing moles of magnesium cancel, and we would have 1.01 times 10 to the 24th power magnesium atoms. Now we want to look at how many moles of magnesium atoms are present in 73.4 grams of magnesium. So we take the 73.4 grams of magnesium and we use the atomic weight off the periodic chart divided by 24.31 grams per 1 mole. We get 3.02 moles of magnesium. So that's using each half, put it all together. Let's calculate the number of carbon atoms in 20 grams of carbon. So if we start with 20 grams of carbon, use the atomic weight of carbon, 12.01 grams, divide that into the mass given, and then we're going to use our 6.022 times 10 to the 23rd carbon atoms per 1 mole. Notice the grams and the moles of carbon cancel. We find that we have 1.00 times 10 to the 24th carbon atoms. This has been a brief tutorial on the mole and calculations using grams, moles, and number of atoms of an element.